Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman. I'm the Marketing Director here at the Academy. Today's webinar is titled Landfill Black Goo. What is this stuff and what can we do about it? Our Executive Director, Dr. Daniel Other, will serve as a moderator and will introduce our speaker today. During the presentation, you'll be able to submit a question by clicking on the Q&A icon on the bottom of your screen. We will take some breaks to address the questions, and we'll also address more questions at the end of the presentation. Before we get started, Dr. Other would like to say a few words. Dan, how are you today?
I am fantastic. Hey there, Maria. Everyone, to what I know will be an amazing webinar for an individual who needs no introduction, Dr. Craig Benson. Craig's actually a personal hero of mine. We just had a fantastic visit in person when he was down in Rolla a month or so ago. And when I'm teaching my fundamentals of environmental engineering class to sophomores in civil, architectural, and environmental, I'm always talking with them about the importance of solid waste management. You know, I often explain to them that the plague is a biological threat, but that the true origin is actually garbage. And the solution to garbage is things like the garbage can and the lid and effective solid waste management from the customer to the landfill and beyond. So, Craig, we talk a lot about your work. And I know today's presentation on landfill black goo, what is this stuff and what can we do about it, will be informative and useful to everyone listening now, as well as to those who will enjoy listening to the recording afterwards. Now, some of you who have attended webinars will wonder, why do I have such a different background today? What is this ball cap that I'm wearing? Those are great questions. Today, before we get started with this webinar, let me tell you a little bit about what the Academy has coming up on Thursday, April 10th, 2025. In just 3 short weeks, we'll be gathering in Washington, D.C. for the Academy's annual Spring Celebration of Excellence in Environmental Engineering and Science. Hence my background of the tidal basin and the cherry blossoms and my hat with cherry blossoms for Washington, D.C. For about 3 decades, the Academy's organized our Excellence in Environmental Engineering and Science competition, also known as E3S, where we recognize exceptional projects every year. And this year, we're adding something a little bit new. Yes, we're going to be celebrating our E3S winners. And yes, of course, we're going to celebrate the winners of our individual awards. But this year, we're expanding our event to be a convocation of excellence. What do we mean by convocation? That's just a big fancy word that means formal meeting of an organization, like a university has these usually as part of graduation. And we want our convocation of excellence to celebrate everybody who's doing excellence in environmental engineering and science. We want to recognize the work of our student chapters. We want to recognize the rising stars, those who have been named to members of our 40 under 40. We want to recognize everyone who's achieved board certification in 2024, as well as some sister organizations like the scholarship winners for the Environmental Engineering and Science Foundation. So for this year, for 2025, we have a luncheon and the E3S Awards ceremony scheduled for a technical program hosted by our friends at George Washington University. And in the evening of April 10th, we'll host our first ever convocation at the Marriott in Crystal City, right next to the Reagan National Airport, just across the river from downtown DC. The convocation dinner is the place where we'll recognize individual award winners, as well as recently board certified engineers, engineering members, and scientists. All this to say, please sign up to join us on Thursday, April 10th, 2025, with lunch from 11 to 3 Eastern and dinner that evening at the Marriott. We can't wait to have you join us. And now let's pivot to focus on today's main event, our webinar. As we begin all Academy programming, including our highly effective webinars, we take a moment to pause and say thank you to our patrons. Patrons are utilities and firms who financially support the programs of the Academy. And when you get a chance, please say thanks to these folks for stepping up financially to support the Academy. If you'd like to learn more about how your organization can sponsor a webinar or how you can get involved as a patron, please let Marissa or I know. We're happy to answer questions and explain the value proposition. And finally, today, it is my privilege to introduce Dr. Craig Benson. Craig is the Academy's CAPI Distinguished Lecturer. His awards are numerous. His impact is far-reaching. But more than that, Craig is a thoughtful and kind person. He's always open to meeting new people, sharing his views, and engaging with those around him. All in all, he has been an amazing ambassador for our profession. And I'd like to mention at the start, he's a personal hero because he's an all-around good person. As Craig delivers his presentation today, I remind you that I have the privilege of moderating a question and answer event at the end of the presentation, so it would be great if you would share your questions in the QA panel so that I can use those to direct today's discussion. And now, with those instructions and with that introduction, Dr. Benson, my friend, the stage is yours. We are so excited to have you here with us. Thank you.
Thank you, Dan. It's a pleasure to be here, and thank you to all the patrons as well. As I look at the list here, I've worked with every one of these firms and agencies during my career, and thank you so much for supporting what the organization is doing. I'm going to talk to you today about what I think is an interesting topic, and hopefully you will too. Black goo, what is this stuff and what can we do about it? I've spent my career working more broadly in waste containment systems and solid waste. And one of the things I've found is about every 5 years, we have some new and really interesting problem that we don't know what to do about in our industry. And as an engineer, that's a great opportunity. It's a forensic or sleuthing type of problem solving opportunity to figure out what's going on and then how do we work around it and create a solution. And this is one of those that's been more recent and I found to be pretty fascinating and actually leveraged a lot of other things that I had been learning about in other areas over the last 15 years or so. Before I begin, I wanted to say a little bit about this gentleman here, Mehmet Yilmaz, who was a postdoc of mine and then an assistant professor at Southern Illinois University. He was really seminal on a lot of the work that we were doing in the first part of this project. And a lot of his intellectual contributions are in this today. Unfortunately, he underwent a really aggressive cancer. And within 4 months, he was taken from us and from this world and from his family. So I want to just acknowledge his contributions here and how much we respect what he's done and how much we miss him as well. Mehmet really was a wonderful man. Just other folks involved in this. The professors normally do the talking, but as you know, there's a lot of people doing work in the background. Mehmet is one of those. Another person at UTAN who's a former PhD student of mine and now a postdoctoral associate. My colleague, Sabrina Bradshaw, who's a research scientist, and my other colleague, Tensoretto at the University of Wisconsin, who's a professor emeritus as well. We all have been working on this topic for several years together. And this was sponsored by EREF, the Solid Waste Communities Foundation for Research and Education. So what is this stuff? I first ran into black goo about 2015. I was working on a landfill in South Carolina. We had terrible troubles with odors at this site. It was watered in, and one of the methodologies to enhance gas collection is to get water out of the waste so we can get the gas moving. Whole fleet of dual phase extraction wells, essentially like a groundwater well, but put right into the waste. A whole fleet of those were installed in the landfill with pumps on them to pull the leachate out with the idea of freeing up pore space to remove gas. And if we remove gas, we would remove the odors. And one of the things that we encountered at this site was that the pumps that were down in the waste would operate for about a day or maybe 2 days, and then they would fail. And when we would pull the pumps out, they'd be covered with this black, sticky goop. And at first I thought, well, it's just something weird about this site, some unusual thing in the waste stream. And I started talking about this with other people, and well, I ran into another site, and then another site, and then another site. And I think today, about one person a week, a new person contacts me a week dealing with this particular issue. It has become ubiquitous in the solid waste industry, not only in North America, but globally as well, as I'll illustrate in a little bit. But this is the black, sticky gunk that is causing all this trouble. Here, I've got a leachate pump from a side slope riser. You can see the inlet on it is just covered with goop. Here's a screen on an inlet completely filled with goop. You can see over here, this is a dual phase extraction well riser The pump's been pulled out, and all this black goop here laying on the ground was pulled out of the well. Here's a force main down here in the lower left, completely full of this stuff. And over here on the right, I find this one really interesting. This is a dual phase extraction pump that was down in the well for 1 hour, and completely covered with this stuff and no longer operational. Now, these are not trivial exercises to put dual phase extraction wells in and to run them. There's a lot of capital, a lot of O&M that goes into this, and it's done for a reason, because sites need to get the leachate out to manage other ancillary issues. And yet the problems of implementing those strategies are compounded just immensely with the presence of this black goo. Essentially can render a well field almost inoperable. So I wanted to figure out, what is this stuff? And then once we figure out what it is, what can we do about it? And we've done a lot better at figuring out what it is than precisely what to do about it, but we'll talk about both today. What are some of the characteristics of this stuff? Well, it's sticky, stretchy, rubbery. It's got a strong odor. It's been in a reducing environment. It's got this classic sulfur smell to it. And you can see over here, this little video I'm showing. I hope that's coming through clearly over the virtual meeting here. But you can see how stretchy this stuff is and sticky it is. And over on the left here, you can just see this nasty, goopy type stuff. What's interesting is that we see similar material in lots of different landfills. And we've looked at 28 different landfills, mainly in North America, but around the world, and see similar stuff. Similar stuff has similar visual, textural, and olfactory characteristics. Where do we see this? As I indicated, we've been focused primarily in the continental US and North America more broadly. And a lot of our sites where we see this are in wetter locations, typically east of the 100th meridian in the United States, where things are more humid. We've got more leachate, and so we've got more issues with moisture and waste, and we've got more carriers for these things. But we have some in the West, actually, a recent one actually from the Portland area or out here, but not only in the US. That's an important attribute of one. Waterloo in Canada, in Ontario, just across the border, also has this same issue, but also in the US territories of Puerto Rico and Guam. And if we travel south of the border and down into South America, we see this in Brazil, in Argentina. People have been calling me from these countries, sending me photographs. I have this stuff. What do I do about it? Just most recently in Finland, somebody sent me an email, sent me a photograph. I heard you know about black goo. What is this stuff? What can we do about it? Fascinating, fascinating. Just some examples. I showed the photograph earlier from one in the US, but here's one from Brazil. That's nasty looking stuff. Yuck. And then this most recent one, these samples we got from Finland. And you could see this force main here. The whole thing's filled with this stuff, and it's just oozing out when they pull the plate off. It's just nasty and really, really problematic from a infrastructure point of view of trying to keep that operation running. Messy. So, how do we solve this problem? First of all, we're going to figure out what is this stuff? What's causing the problem? And that, to me, that's the foundation to everything we do. We have to understand what we're dealing with. And so we began in that direction. And I have to admit, I have been fiddling with some similar types of materials with similar rheology, and I've been using some of the tools I'll be talking about today, and I adopted them and brought them over. They turned out to work out pretty well. I call these forensic chemistry tools. One of these is FTIR. I imagine many of you are very familiar with FTIR. Essentially, and if I put this in a very simple way, we're going to impinge on our sample of goo an infrared light or a beam of infrared light, and that will interact with the molecular structure in our goo, particularly in the bond of different bond structures in our goo will cause different amounts of absorption of different wavelengths of that light and some of it will be transmitted through and other won't. And we'll process that light that is transmitted through the specimen. We'll process that and we'll get a so-called FTIR spectrum. And that essentially is provides us a chemical fingerprint of sorts. Really easy to run tool, and really helpful, and particularly if you have an FTIR instrument that has a library in it where somebody's compiled the FTIR spectra of all these different materials. You can begin to say, oh, I'll look in the library. Oh, I'm likely one of these 5 things that are in the library. And that's very helpful. Another tool we used, a little more sophisticated and not something that's always on the bench top, is solid state NMR, or nuclear magnetic resonance. Essentially, what we're going to do is apply a constant magnetic field and in a weak oscillating field, and that will perturb the system and create a response that's characteristic of the particular bond structures in our material. And so we'll get a spectrum out of that too, which also tell us about composition of the goo. I don't use this as much as I use FTIR, but this is a similar type of tool conceptually, that it's going to be sensitive to bond structure. And we could use 2 independent measurements and begin to see where similar things are. So let's take a look at what we got out of those two tools. And I'm going to talk about another one in a minute. This is where it really got interesting. I'm collecting black goos, originally just from largely around North America, but then we started getting them from Guam and Puerto Rico and from South America and now from Finland. And when I run FTIR on these samples that come out of the bowels of a landfill, they're remarkably similar. They're really similar. And I look at the peaks in the spectra. And here I'm showing spectra from a whole collection of different goos in our portfolio. And wow, these are from landfills all over the world. And look at how similar they are. Yeah, they're a little different here and there, but particularly these major peaks corresponding to specific bond structures are very, very characteristic and similar in each of these materials. Remarkable similarity in the bond structures I show up here corresponding to different peaks will turn out to have some importance in identifying what the material is. But remarkable, all these different materials. And so this told us that we were looking at something similar in all these different sites, which is causing the problem. We look at our NMR work and we have similar outcomes. This just amazed me. The NMR spectra for these goos from all over the place had this level of similarity, with the peaks in the spectra that reproducible. Of course, the amplitude varies from site to site, but just the remarkable similarity, I found it just striking. This also told us we were onto something, that there was some part of the waste stream that was going into these facilities that was creating this stuff in the bowels of the landfill, and the leachate collection system, the pumps and the sumps, that was very similar at all these sites all around the world. So another tool that we use, and those are 2 very sophisticated tools, are FTIR and NMR. Another forensic chemistry tool, as I call it, is TGA, or thermogravimetric analysis. So I think of the FTIR and the NMR as very sophisticated techniques, and I think of TGA as just brute force analysis. TGA, what we're going to do is we take our sample, we're going to put it in a nitrogen atmosphere so it doesn't have oxidation to combust, and then we're going to heat it up. We're going to ramp up the temperature from room temperature at 20 degrees C up to 1,000 degrees C. And then we just look at the waste loss, the weight loss in that specimen as a function of temperature. Just brute force analysis. I'm going to heat it up, I'm going to put energy into it and bust bonds. And what do we see? Look at these TGA spectra. Just remarkable in my mind. These are from goos from all around the world, and yet they're very, very similar. They lose some mass early on. Some of that's some water, although I got to be careful because these were all dry. So this is not water. This is probably some other organic components. But then around 500 degrees C, it plummets, right? There's a steep drop in the mass, and that's due to composition of these so-called synthetic polymers. And this is important. These are synthetic polymers decomposing. Typically, they'll decompose in this region of 500 degrees C, and then a secondary decomposition closer to 700 degrees C. This is important because this the common thinking in the landfills, I've got black stuff and it's clogging, it must be biomass. That's the conventional conclusion. It's black, that means it's biological, and it's in a landfill, it must be biological, it must be biomass. Well, this would suggest I have black, sticky, clogging stuff in my landfill, but it's not biological because natural biopolymers would decompose at much lower temperatures on the order of 200 to 300 degrees C. And we'll see some of that in a few moments. Nature creates weaker bonds because nature wants to reconstitute and recycle polymers in the environment. We create synthetic polymer structures to be much more robust because we want to engineer them to do certain functional things, and we don't want them to break down readily. So this is an important clue. These are not biomass. These are not biological polymers. These are synthetic polymers, all right? And they're very, very similar for all these different sites that we're looking at. So let's just look at that question for a little bit more. This whole abiotic versus biotic question early on was a big topic of debate. And so one of the things that we did to look at this was just to do some analysis on black goo from a site and then some biomass from a site. And this at this particular site, I won't mention it, but they have been doing well, I can mention this is at Waterloo, and Laura Hugg was of the University of Waterloo was very helpful in sharing materials and samples with me. And they've been studying the interactions of biological phenomena with black goo, and they have been creating biomass at their site for comparative purposes. And so she sent me a sample of her biomass and their black goo, and we analyzed both of them in similar ways. Just to get a sense for is the black goo similar to biomass, or is it quite a bit different? As you can tell already, I'm suggesting it's quite a bit different, but this provided us with more facts rather than just me saying that. And here's a comparison. Here's the FTIR spectra. Again, these are represented a little bit differently. The gray lines are what we call dry black goo. Early on, we were running our FTIR just in the samples that we would get. Later, we've been drying the samples and running FTIR to reduce the effects of water. And then we've also been doing experiments on rehydrated black goo. So it's been dried and then rehydrated and dried again. And I'll talk a little bit more about why we did that later. But you can see that the black goo samples in the background, just dry black goo, those are the gray lines, ones I showed earlier. And then ones I've rehydrated in gold. But importantly, our biomass samples in blue and red. And then what we call black goo 8, that's actually in our FTIR library now. We have a black goo in FTIR library in our lab, and that's here in black. And you can see the FTIR spectra. There's some similar threads, but the spectra actually are quite a bit different between the biomass and the black goo. Similarly, if we do TGA on the black goos and the biomass, they're very, very different. As we show here, the biomass decomposes at much lower temperatures, exactly what we'd expect, because it has weaker bonds because nature wants to recycle things, whereas in engineered chemical products, we want them to be resilient and robust, at least during their operational life. Might be actually good if they broke down a little more readily in the landfill, but that's a story for another day. So this evidence with the other information really suggested what we're dealing with synthetic polymers in our waste streams. They tend to be fairly similar from around the world. And the question then is, what are they? Where are they coming from? And why are we seeing this now? I've seen this for about the last 10 years. I didn't see it before that, and I don't think anybody else had, not in a substantive way. Well, one of the things that we started doing, and this is, it's like so many things in science and engineering, you're just fiddling around with it. Well, let's try something. Let's see what happens. It's so often in my career when let's just try some crazy experiment, see what happens. We always learn a whole bunch of new things from that. And this is an example of one. We were drying the goo, and they said, let's see what happens when we put some DI water in it and let it rehydrate. This is where it got really interesting. So we took a dried sample, like I showed here, and then a wet sample we rehydrated it with DI water, and the black component of the goo essentially became like a rind, and it just peeled off. And the internal piece of it was this jelly type material, this kind of translucent jelly type stuff right here. All right, and that suggested to me what we were seeing, the black component, that was probably just some sulfides and other material that got mixed in with this broader gelatinous stuff that's in the interior. And the black part really was just a consequence of being in the landfill and that reducing biological environment. And uh, just a coating or a colorant of sorts. But what was really interesting is this jelly type stuff looked a lot like hydrophilic polymers that we had been dealing with in other applications. Um, and so we took that polymer set, we took out the jelly part and did more analysis on it. Just examples of that. Here you can see this was black goo from a landfill. We separated it through these rehydration experiments. And here we're just getting this almost transparent jelly type stuff. And over here on the right, this is actually Mamet's hand showing this jelly specimen of goo rehydrated with DI water. Looks just like a gel, pretty remarkable. And looked like some of the synthetic hydrophilic polymers we had been studying for a completely different application before. So things that we learned from this, we've got these bond structures up here that I show at the top. We've got a high temperature decomposition, which suggests it's synthetic, high organic content, that's kind of obvious. It's got high water content, it's hydrophilic, so it likes to bind water. It's a polymer, but it likes to bind water. Appears to be predominantly abiotic. Has this firm, stretchy, elastic texture to it. And then on rehydration, it's this clear gelatinous stuff. And many of these characteristics are what we see for acrylate-based superabsorbent polymers, something that we use in everyday life all the time. Remember, a landfill is a waste repository. You're at your home. I'm in my home right now, and I took out the trash this morning. Our hauling company came by just a little while ago to take it. All the stuff that I've been using and is now has no value, either is going to go get recycled, hopefully, but a lot of things can't get recycled. They go into our garbage, right? And that garbage then goes to our landfill, and that landfill has all the stuff that we don't want anymore. And it's managing it and protecting the environment. And the impacts of all the stuff we put in it end up in the things that we have to manage and operate at those sites, like black goo. This is coming out of the waste stream, probably in your house and my house and everybody else's house. So we started to go down this path of kind of looking at things, superabsorbent polymers, because of the characteristic, and starting to think about where are these things used outside of the very technical application I had before. Now I have a wonderful young granddaughter, 13 months old, and she uses a lot of superabsorbent polymer all the time. Diapers. Diapers are about 85% of the mass of superabsorbent polymer made in North America and just about any country around the world on an annual basis. They go into diapers. Superabsorbent polymers like polyacrylate, sodium polyacrylate, they're a particulate material. They bind water like crazy. They bind, and they can do it in a strong salt solution. Great for diapers, right? And so we bought diapers, and we did experiments on that dry particulate. Here's an example of it, hydrated with deionized water in a beaker. Ooh, that looks a lot like our rehydrated goo. Not too different, right? And then we bought sodium polyacrylate just directly from a vendor. Again, we took that sodium polyacrylate and we mixed it with deionized water, got a nice jelly type structure, and looks not too different, cleaner than our rehydrated goo, but still, at least from a physical perspective, looks very, very similar. Now, one thing I should point out that diaper absorbents often are polyacrylates, but other stuff too. And so sometimes you'll get linear polymers, sometimes it'll be cross-linked polymers, a blend of polymers, depending on what the particular company is trying to market in their products. So sodium polyacrylate is just one of those, but probably is the most common superabsorbent polymer. Where do we use this stuff besides diapers? Well, diapers is one, but feminine sanitary pads is another, pet pads, meat pads. This is when I was having our holiday barbecue last July 4th, and I was out there on the barbecue and I'd taken the steaks off the pad I got from the butcher, and I started looking at this dry lock pad, and it turned out this stuff has superabsorbent polymer, and it's great for absorbing the moisture that's in a salt solution. It's just fantastic. Another one's paint hardener, latex paints. If you're going to discard old latex paint, you have to solidify it first because we can only take solid waste paint. Go to the hardware store. I'll show you in a minute. It's latex paints. Hardeners are superabsorbent polymers, dewatering agents for dread sediments. We use these in wastewater plants as flocculating agents. Interestingly enough, they're used as drilling slurries, but some drillers in landfills for gas wells will use these to support the waste mass during drilling. Not a good idea if we want to keep our gas wells flowing to be putting this sticky clogging stuff in it. Water locks in gardening, water and cable blocks, these growing toys that kids have for growing plants will have these. It just all kinds of different things have they're ubiquitous. Never knew how common they were. This is one that just struck me. I was at Menards and I had to buy some paint harder because I had to get rid of some latex paint I had. And I said, I'll just take a look at what this stuff is. I'm working on black goo and I'm always looking at stuff. I turned it over. It's sodium polyacrylate, right? That's what it is. Stick it in your paint, stir it up, and it absorbs the water molecules and it hardens very quickly. So what are these things? Super absorbent polymers, that's the broader name, from 12.2 billion tons produced in 2020. Water soluble hydrophilic, they'll bind 100 to 1,000 times their mass in water. That's what makes them so helpful. You can see one working over here on the right in this little video. Goes from dry to fluffing up with moisture. Diapers, sanitary products, I mentioned before, different applications, but 85% by mass are used in low fluff diapers that go to landfills. 85%. So a lot of that's going into landfills. And sodium polyacrylate, as I mentioned, is the most common of the superabsorbent polymers. So one of the things you say, well, that's a hypothesis. We think that's what this stuff is, and that's probably where it's coming from. Let's go buy some of it, like I showed in those hydration experiments just a minute ago, and let's start doing the same analysis on it. Let's do FTIR, let's do TGA, let's do NMR, and let's compare it to our black goos. And you can see black goo 8 here. That's the one in our FTIR spectrum we use as our kind of base case. Here's polyacrylate that I purchased commercially, I showed earlier. 2 different brands of diapers, HG and PG, manufacturers not to be named. Paint hardener, feminine sanitary pad as well. And you can see, wow, the TGA records are just remarkably similar. The gray lines and the gold lines are for our goos, our broad collection of goos. The yellows are the rehydrated goos from those dry and then re-wet experiments. And one of the things that does when we re-wetted those is that the black goopy film is coming off. So we're getting much more like a pure material. And you can see how sharper the TGA spectrum is from those rehydrated goos, because we've gotten a lot of the impurities out. We're looking more at just what that is. And wow, I mean, just look at how similar they are to the these commercial products and polyacrylate. Wow. Same thing with the FTIR spectrum. You look at the peaks in it, Again, wow, remarkable how similar they are. Very likely this is the source. Do some SEM, just looking at different lines of evidence to check to see if we're in the right vein here. This is just polymer from black goo that we've isolated and we've run SEM on. And then here's some of the sodium polyacrylate. Again, this is some of Mehmet's work. Thank you to Mehmet for doing this. Again, morphologically very similar as well. So all this pointed to this is the likely source. It's likely the diapers and similar types of things that are in our waste stream that are ubiquitous and now are showing up in our leachate collection systems and causing us a plethora of problems, particularly at wetter sites where these are more mobile. That's still a hypothesis. So we did a couple other things, and we created waste columns in our lab. We like to create big columns and physical experiments. And we took MSW from Dane County Landfill, which is near the University of Wisconsin, just about 10 miles away. We got that waste, we shredded it, brought it back, put it in a column that was about 20 centimeters in diameter and about 20 centimeters tall. We wrapped it in a heating blanket so we could simulate conditions in our landfill, ran it at 55 degrees C, and then we spiked it. When we put the waste in there, we spiked it with sodium polyacrylate in the waste stream. And then we took leachate from the landfill and dosed this periodically like it might experience in the field. And these experiments are always fun and nasty too. After we started off, we have leachate through there very quickly. Became reducing. We had a nice black mass inside, getting the brown black leachate coming out the bottom. What we expected. Very quickly became and our gas composition as well as what we would expect for a reducing environment with anaerobic bacteria. Looked at our leachate, brown stuff with little black particles in it. And we can see in our effluent tubes, we had a black coating in it. And then we go in and scrape out some of that stuff from the tube. And this black sticky stuff we're generating. It looks like black goo. Not as much mass as I showed earlier, but similar type stuff. And we run FTIR on this. I apologize, this graph is not quite as clean as some of the others. But one of the things that we see is here's our blue line. That's our FTIR spectra from our column test from the goo from the column. And then I just have different black goos from actual sites shown here. And you can see the same type of, the spectra are very, very similar. Similar peaks in the spectra from our actual black goos and the black goo from the effluent from our column test in the lab that was spiked with 5% polyacrylate. At least suggests after 50 days of testing the polyacrylate that the stuff that was coming out appeared to be polyacrylate, very similar to what we had been seeing at lots and lots of sites around the country and also around the world. TGA showed similar things. The TGA spectra from the column goo was very similar to what we're seeing for the black goos as well. So similar type of conclusion here. I should point out that, so one of the things that we're seeing is that one, these all do seem to be superabsorbent polymers. Sodium polyacrylate's probably one of the predominant ones. That they seem to be sourced from a lot of commercial products, but probably the personal products, diapers, feminine products, things like that are probably the most ubiquitous sources. And those are things that are always being thrown out in our solid waste stream and into our landfills. So it's not surprising that they end up in our leachate collection systems and other components where things are very difficult. I want to point out, though, that one of the things that we do see is that there's other black liquids around that come from other sources. Everything that's black and clogs things and is abiotic is not necessarily black goo. For example, this is from an elevated temperature landfill on the right, this black liquid. This was sent to me saying, is this black goo? And we did our analysis on it. No, this is something different. Another site, they sent us this stuff that had been clogging their sewer line that was taking leachate from the landfill, and it was asphalt. It had nothing to do with anything coming out of the landfill. So not everything black is black goo. You need to analyze it and determine whether that's the case. So we have a good handle on what this stuff is. And the question now is really what do we do about it? And that's the area we're working on. I'll tell you, we don't have a great set of answers on this yet. One of the things that's been found in practice that works well is essentially using a strong acid solution. This is one that's AC 6400 that's being used in practice. Essentially, we're just going in there, applying acid and blowing up the molecules. 20% acid solution, put in the sump, flush it out in a warm solution, hot water solution into the leachate collection system and flush this stuff out. The hot water, I think, is important because the rheology of this stuff, as I'll talk about in a bit, is temperature dependent. And so the hot flush that's being used may be just as important as the acid. The trouble with these treatments is they treat the system and fix it intermittently. But the problems come back because it's coming out of the waste mass, right? And it's coming back into our system. And we haven't resolved the problem. We've just resolved some of the impacts of the problem, and they're temporary. And this is a very costly cleaning process, and it has other health and safety issues. It's just nasty to do. You've got different off passes you have to be very careful about. There are vendors that are very good at this. Progressive Environmental is probably the leader in this these days. Other things that we've learned, which I think really go towards more longer term issues that we can incorporate in design, is one of the things that we found is these goos tend to accumulate in cooler, more quiescent zones. Leachate collection system on the surface liner, liquid that's flowing down under gravity, right? It's a unit gradient. It's essentially flowing downward and then hits the floor. And the gradient on the floor is 3%. It's not 1, it's 0.03, right? Now the stone is more permeable than the waste, but still it's a lower energy environment. And the polyacrylates that are dissolved in solution as they're flowing down will begin to coalesce or almost stick together. They stay mobile as they're flowing downward because they're shearing, right? We've got shear stresses in the fluid. And as those shear stresses diminish, the molecules have greater propensity to coalesce. At least that's our hypothesis. So in these low energy environments, leachate sumps, check valves, pump chambers, even dual phase extraction pumps, because the pumps, they pump and then they turn off and they sit for a while. They pump and sit. And when they're sitting, it's quiescent and the molecules can begin to stick together. The other thing is temperature. Like on the floor of the landfill, in our leachate sump, in our pump chamber, we're at 10 degrees C, right? In the landfill, we're at 55. And what we've seen is that the rheology of these is very temperature sensitive. As the temperature cools, they tend to agglomerate and become much more sticky and viscous at lower temperature. So messages here, one is we got to keep the shear stresses up. We got to keep this stuff moving. And we might be able to do some more things with hot water flushes or getting temperatures up to get things mobile. But we think about design going forward, we put things at low flat slopes to maximize airspace, but maybe we ought to be thinking about keeping slopes and things like that to higher so that we can keep the velocity of the leachate moving faster to keep the shear stresses up to eliminate some of these problems. These are ideas right now, they're hypotheses, these aren't facts, but things that we've been working on. So in summary, what have we learned? Our forensic chemical analysis suggests that these are predominantly hydrophilic superabsorbent polymers, polyacrylates, probably polyacrylamides, probably mixtures of those. That's the predominant component. We didn't know this 10 years ago. We just had black stuff sticking in pumps. We used the tools that we have available in our laboratories to begin to explore these materials and study what they are. And this is what we believe their primary components are. Lines of evidence point in that direction. The black component appears to be really an ancillary component. It's really a component that the sticky goo has picked up, other biological and other sulfides and the like that are in our leachate, and it's sticking along with the goo. And we've seen that and when we re-wet things, that just peels off. So that's really just an ancillary component from our reducing environment and not an intrinsic component. They're largely abiotic. They're synthetic polymers. But one thing I want to point out, and one of the things that Laura Hug of Waterloo has shed some light on and some really good ideas about, is that the microbial communities in which the black goos exist they're probably living on the surface our goos, and we're breaking bonds as those communities essentially feed off of our goo, and that may be contributing to the stickiness and the stretchiness as well. So while it's abiotic in basic composition, the microbial component may be very important. I've been largely abiotic my whole life, so that's an area where I look forward to collaborating with Laura and others in the future. Breaking down the stuff's complicated. These are tough molecules. They've been designed to be tough and resilient because we use them in difficult environments in our homes and businesses. They stay that way in the field too, and they're difficult to break down in the landfill, hard to flush out. The techniques that we've been using right now are just brute force destruction with acids and hot water. Probably can do something better. Ultimately, we need to find a way to keep them in the waste and out of the leachate collection systems and pumps. We haven't figured that out yet. Right now, there's no magic solution. We know there's a problem. I don't have a solution for all of this right now, but these are just ubiquitous. They're in every one of our homes. They're in our schools and our offices, and they end up in our waste stream. But one thing we do know is that they are rheologically sensitive, and the shear stresses are important. So keeping them moving will help, and keeping the temperature up will help as well. So that's what we found. This is, like I indicated early on, in the landfill industry, every 5 years is some new, interesting, weird problem that pops up that we never thought about before. Elevated temperature landfills is another one that I spoke about in my CAPI lecture. I've been fortunate to be in the middle of trying to figure out what these problems are, and working both as an academic, but also with people in industry, which have been great collaborators. And what fun things it is to take science and engineering and apply it to practical problems and create solutions. Appreciate the opportunity to come here and talk about it. I think that may be my last slide, and I'll go to our Academy slide here at the end. Dan?
Fantastic. Thank you, Craig. We appreciate it. We appreciate it. If I can actually beg you to maybe we'll pause the slide, the screen share, because then people can see the smiling faces as we have a little bit of discussion. If that's an easy thing to do.
Sure, you want me to? I can stop that. Sure,
Yeah,
I love to see the faces.
great. Then
Yeah.
people can see us for the conversations. Fantastic. I love the technical term, black goo. I mean, nothing like talking like the solid waste folks. It's where I was like saying at the beginning, I explained to my students, right? Like 500 years ago, we're dying from the plague. How do we solve it? The garbage can and solid waste collection, right? So, it's like,
Yeah.
let's just be practical here. So we got some questions that came up. I'm gonna kind of like lay out kind of the stuff to talk about. There'll be some more that'll come in, but this will help us kind of like, you to hear the whole questions, and then you can be able to kind of go through and answer them. So
Great.
it's really clear that you were talking about lines of evidence to try to understand that. So that's good for, kind of students and emerging professionals to pick up on. You talked about time, you talked about forensic tools, you talked about, looking at some of the synthetic versus biological. So one of the ones that people were asking about, this kind of like 10 years ago, whether that's, some of us as we get older, 10 years becomes, like 50 years, 10 years. So, if we're talking like 2010, somewhere in that range. So some questions are like, what other things are out there? Is that when we started really getting into these diapers? So folks were kind of
Yeah.
asking about that. You talked about, FTIR and some other forensics. Folks were particularly asking about GCMS and some folks, some stuff
Yeah.
around that. You're talking about that this seems like it's synthetic rather than biological, right? So what about the other kinds of sources that we might, if we've got biosolids coming, that are coming from
Yeah.
our wastewater facility and we're putting that in, is it the polymer for dewatering? There's all these other things. There's the kitty litters and all the alternatives to the kitty litters. There's all this artificial ice that is in our packaging, right? That's like now we get like the meals delivered to our, everything comes in and it's got, we keep getting better and better versions of this like recyclable artificial packaging, but is some of that still landing in solid waste stream? And so, what are the other things that this might be coming from? It's interesting that you talked about starting to think about a mass balance, like how much of this stuff is used. So one question would be other places that it might end up, right? Plastic ocean, right? Like where does it, do we find it in other places as well? Does it sink? Does it float? So, are there any threats from the polyacrylates? I mean, like it's obviously in diapers. We think it's okay to be next to a kid's skin, but does it naturally break down? We thought PFAS was safe until we put it on every cooking surface and discovered maybe not. So, we've got this stuff in our diapers next to our kids' skin. Is it really that safe? Is there any stuff known about the toxicity of this? Now we get into the landfill itself, right? So how does it mobilize out of the, it's in this diaper. How does it get out of that and end up then in the leachate? You're talking about like, well, we could hit it with some heat, we could hit it with some acid, but how about that heat and acid come in for the leachate treatment systems or the leachate recycling? You mentioned the operator safety, all of the important kind of issues to think about. So there's some other questions that have kind of come in, which we'll integrate in there. But that's kind of the where we'll start with some of these, and then we'll drill down to some as folks are peeling them in. So if we go back to the lines of evidence, right? So okay, so you started seeing this stuff like about when and how does that relate to products that you'd be seeing up here in the solid waste stream?
Yeah, good question. So, and I first saw this, it was about 2015, roughly. So 10 years ago. And at the time that I mentioned, had these gas wells are getting fouled, and this black sticky stuff on there. First time I had seen it, and that's where I said, "Oh, this is black goo." We didn't even know what was it called, black goo. That's where then I'm amazed the name stuck. But that was about the first time. I mean, one of the things that we know in our systems is that the things that we see today often have origins 10 years back, 15 years back. And if you go back into superabsorbent polymers first started coming on the market in the early 1990s, the ones that we're talking about here, I think actually started in Japan. But the growth in the volume of the mass produced of these materials has just been exponential. So they've been produced and used in increasingly greater quantities over the last 25, 30 years. And they end up in our landfills. And then, 10 years later, they end up causing problems. Now, that's all pretty rough. And we haven't kind of done a detailed forensic history that sure would be interesting to do. We've been talking about this in our research meetings and trying to go back and look at all the origins of this, but we don't know for sure. But one of the things I have seen in my career, all the problems that we have, often the really complicated ones have origins that are a decade before, sometimes 2 decades back, and then they show up in our systems later on as they kind of make their way out. Most of the things with elevated temperature landfills, the origins were 20 years before they got hot.
Got it. So the question about like that current packaging we've got for these alternatives to ice and all that, the next generation will deal with that problem, right? Okay, this is the diaper problem. Okay.
Yeah, probably. Yeah, but some things may occur quicker. That's just been my experience. We haven't really looked at the temporal component to it, but I've just been amazed at how ubiquitous these materials are in economy in our everyday life, these
No,
superabsorbent polymers. And they're
fascinating.
great stuff.
Yeah, no, I mean, yeah, exactly. Anybody that's
Yeah.
ever changed a diaper versus a cloth diaper, you're like, I get it.
Yeah.
I get it, right?
Yeah.
GCMS, other kinds of forensic tools that have been used to kind of tease these apart some?
We've primarily focused on those that we've looked at. We've actually talked about doing a more fundamental analysis with GCMS. We haven't done that. We haven't felt the need to do it yet, but that would be a logical next step to kind of drill down deeper into these materials to really strengthen the facts around the proof of the hypothesis, right? Interestingly enough, we have all these nice, wonderful instruments and laboratories, and one of our labs, they were fine having us analyze polyacrylates. When they found out it came from a landfill, no longer can bring it in our lab. Verboten.
Yeah. For those of us that are in biological, we always name it a marine sample because nobody has a
Yeah.
problem with a marine sample. Just don't bring sewage sludge in and out of a country or something. But yeah,
Yeah.
marine sample, no
Yeah.
problem.
Yeah.
What now? How about other things that our audience might be running into, like the dewatering polymers
Yep.
that would be in biosolids? Are those in the similar family or very different or?
Actually, very similar. One of the examples I showed earlier, one of my first slides, I talked about this dual phase extraction pump that had been operating for an hour and was coated with black goo. That's a site in central Wisconsin that has largely taken dredge sediments from the Fox River. Fox River was dredged for PCB contamination. And superabsorbent polymers were used to essentially bind the water in that so that it could be managed as a solid waste, right?
Sure.
Pass the paint filter test. And that cell is almost completely filled with dredge sediments. So I've seen the same thing with wastewater treatment solids, and I think that's one of the sources as well. Another thing, 20 years ago, we land applied a lot of our biosolids, right? And as different contaminants became a concern, PFAS one of those, landfill started taking a lot more of our biosolids and stopped, and land application really diminished. And so the biosolids contribution to the solid waste stream has increased a lot. And I do think that's probably one of the pathways as well. That's definitely a contributor.
Makes sense.
We've asked some treatment plant operators to send us their polymer additives, and they're superabsorbent polymers, just like those I showed. Very similar. Yeah.
Okay.
So I do think that's the source. Yeah.
Okay, makes sense. Now we had one detailed question on one of the slides. We were talking about quantity, and I think there was around 12 billion tons or something. I thought I took off the slide because somebody asked, "Is that 12 billion tons or 12 billion pounds?" So I don't know.
I was wondering that too.
Okay, fair enough. So we
I
do
think
realize.
it's pounds.
Okay,
Yeah.
we realize there's an extra 3 zeros on those two numbers, but it's the 12 we've
It's a
got.
lot.
Okay,
Yeah.
it's a lot. Okay, so
Yeah.
it's either
Yeah.
a lot or a really lot. Okay, so
Yeah.
fair,
I was thinking
fair
about
enough.
exactly. I'm thinking 12 billion tons. That can't be right. That's a lot
It
of
sounds
stuff.
like a lot. It sounds like a
Yeah.
really lot. So,
Yeah.
how about now? And this might be outside of your immediate experience, but if we hang with these polymers, right? So plastic oceans, right? Because I mean the diapers don't all end up being caught somewhere. We get plastic bags everywhere. We get water bottles everywhere. Does this stuff tend to sink, float, move around? Any thoughts on where we would end up seeing these polymers in the environment in general if they don't get caught in our solid waste streams?
Yeah, well, I do think we're going to see them in lots of other places, right? Because not everything, gets in the trash. In fact, a lot of stuff doesn't get in the trash. Those of us in the environmental business, we tend to be a lot more conscientious than many of our neighbors are, and it sinks. So in waterways, it will be on the floor, and
Okay.
it will sticks to stuff too. So you're going to pick up solids and other things that are going to bring up this specific gravity and the density of the material, and make it even more have a greater propensity to sink. So it's going to be on the floor,
Okay.
and you're going to have shear stresses along the bottom that are going to break it up and mix it in with everything else.
Lovely.
Yeah.
One comment from somebody was, it kind of looks like snot, and I thought, okay, so it's
Yeah.
fair. Right?
That's a great thing about our business. We got this really nasty stuff to talk about, right?
It goes from black glue to snot. I can appreciate that. So again, and another one that's kind of around this space that might be out of your immediate wheelhouse, but maybe if you can help us understand. Okay, so we've got it next. We've got it everywhere. We've got it next to our kiddos' skin and the diapers and all. Any toxicity, but I mean, we don't design
Yeah.
diapers to be ingested, right? And then biological breakdown of any of this stuff. So any
Yeah.
thoughts or any literature there you can share with us on the potential toxicity as well as the biological breakdown of it?
Yeah. We haven't gone down that path in a substantive way. This does concern me, though, is that we make an assumption that things are safe, right? And often that's just because we don't have any data one way or another. We thought PFAS was great, right? And now maybe we got a Scotch Guard carpet. I saw a sample of Scotch Guard logo in my home the other day. I was like, wow, different era. Wonder product to wonder why we made it, right? So I don't know the answer to that, but these are the types of things that we ought to be asking, right? When we produce new products, we ought to be always looking at that impact. And we don't always. We only look at it unless somebody forces us to, unfortunately.
Yeah, we tend to be in that litigious after the fact, right? Rather than the
Yeah.
precautionary
Yeah.
principle ahead of time. No, so
Yeah.
that's a now we've got a few so then how does it mobilize there in the landfill? You were emphasizing the whole like, well, we got to keep it moving, we got to keep it warm.
Yeah.
Well, that almost seems counterintuitive, right? Because then it feels like it'll mobilize more that we got to keep.
Yeah.
You know what I mean? So can you help us understand that a little bit? Like, how does it get out of the diaper and into the leachate? And then if we're going to keep all that stuff moving, are we just going to make it worse by, like the more we stir it,
Yeah.
the worse it gets? So
Good question. Yeah, in our waste mass, of course, we're like the temperature that's going to be about 55 if things are all healthy anyhow. That's where we want it, and we use that for lots of advantages. We create wonderful renewable natural gas these days in large quantities on all our landfills. Wonderful stuff. So it's gonna be warm. We're not going to change that to demobilize it, you might say. Yeah, but the question is, yeah, how does it actually get mobilized? You think of a diaper and a trash bag, you put it in your bin, but when it goes to the landfill, it dumps out of the truck, and then you're pushing it with a dozer and a landfill compactor. And a landfill compactor's got big footed uh, cleats on the drums, right? That's going on the compactor wheels, and that's there to shear things up, to tear it all up so you can get it as dense as possible. Airspace is king, right? We want to get as much mass in per volume. So it gets sheared up into a mass that can be compacted into as dense as practical. And all those things that were containing it become shredded, right? And then it's just inundated with liquid, right? If you're somewhere in the east and we generate in a sites, you generate 8 inches of leachate a year on the floor, so you've got liquid moving through on a regular basis. And some of the sites, if we've done leachate recirculation, something we don't do so much of these days because of all the problems it caused. But if you got more liquid, and then you just got more things mobilizing it. And the changes in chemistry will alter it as well. Just the ionic strength of the leachate and the relative preponderance, whether it's more sulfate, like the anion ratio really affects the mobility of the polymer. That's in my lingo. Sorry, it's chloride to sulfite ratio. The more chloride rich it is, it tends to be more mobile. It changes the conformation of the polymer.
fair enough.
Yeah.
No, and I appreciate the lingo back and forth. So some additional questions have come in. I'll kind of take us through these. They're in the space, but maybe it helps people get a little bit of their, kind of some of their particular ones in here. So let's move a little bit more into like kind of the policy realm. Do you think that we're gonna like look at disposing of these kinds of materials in a different way in the future? Will we think about it more like we do, I don't know, by analogy, like fats, oils, and greases? I mean, are we gonna segregate? Are we gonna, any thoughts about some of the policy space that we might go with some of these?
Yeah, that's a really good question. That's something I've been on my mind. If I'm an operator and I'm dealing with these problems, they're costly and they're a hassle. I got a contractor coming in to clean this thing out regularly. It's not a one-time fix. It's every 3 month fix, and it's expensive each time. Then I've got leachate problems, and I got my regulators not happy with me, and the cost of that to the business side is significant. And then I've got issues with I can't get water out, and then I've got odor problems, and that creates other problems with my business. What I think will drive this, not so much from the regulatory side, but from the owner side.
Okay.
They're going to say, we're going to increase our waste fees substantially if this stuff stays in the waste stream. If you're going to landfill your garbage at our site, the tipping fee is going to go up because it costs us more to manage it. And then when the community, that goes into taxes, and then people say, "Wow, where's my solid waste tax so damn high?" Oh, okay. Now we're going to separate it. Right? That may be what happens. I think we're going to see something like this because literally 10 years ago, I saw this for the first time, and now I get a call about this every single week. Partly because people know I'm working on it, but every week I get a new site and people from Finland calling me. Wow.
That's pretty far away, right? So
Yeah.
now it was cool that you did like the separation. You separated the goo out. You would do some dehydration, rehydration. We had some technical questions about kind of like, well, exactly what were the temperatures, but we also had kind of like some sustainability questions, like, well, could there actually be a process there for pulling this stuff back out and recycling it? So were there any particular details of the actual process that you used, or a paper that you would reference people to say, hey, here's where we've got every last detail of our process there. But then how would we think about that in a sustainability standpoint? Like, could that be
Yeah.
part of a new innovative process to recycle the goo? We're drinking recycled water. Why not use recycled goo in our diapers, right? I mean, it kind of makes sense from a sustainability standpoint.
Yeah. Why not? And that's the opportunity. I have to admit, it was fairly ad hoc. These rehydration experiments. It was just like, what if we try this? Like so many things in the lab, you're just like, it's kind of doing this. And we've been working with superabsorbent polymers. What if we dry it and rehydrate it? If it's a superabsorbent polymer, it should go.
Right.
And we did. And then we said, wow. And you just see these phase separations too, that was just remarkable how the polymer separated so quickly from all the other stuff. And literally it's all the other stuff because it's been going down through a landfill, picking things up with the gel, right? And
Right.
so you could do a separations process pretty conveniently with that. And then you'd have to treat it, right? Because you've got probably a pretty nasty microbial community on that cube, but why not? I mean, that would be logical and practical. It's whether you can do it from a sustainability perspective. Can you make the economics work, and then start to look at the other parts of the LCA? Is the energy right, and is the greenhouse gas emissions right, and things like that. I would bet you could, though. Then you got to get people to have a separate bin for their diapers, and we'll see how popular that is.
Yeah, any of us that have ever tried cloth diapers know that. I tell you what, the more times you have to touch them, the more you're like, I'm so grateful for disposable, right? Like in the healthcare where people are like, wouldn't it be nice if we had glass instead of plastic? And you're like, I don't know that I want some reused healthcare stuff. I'm kind of fine with single use. So, I don't know. There's those interesting spaces. So from a practical standpoint, the operators, the owners, right? Okay, so higher tipping fee. I don't want to have to deal with it, but now I've already got it. You're saying I'm seeing it everywhere. People are calling me. It's there. So besides some temperature, maybe that helps, some acid, maybe, but how about like ozonation, hydrolysis? Thermal enhancement, ultrasonics. Are you guys in the space of like trying these out? Do you see any trends there? Can you give us any advice on that?
That's all the next frontier. That's what we're working on now. There's lots of opportunity in that space, and it all comes down to kind of thinking about the fundamentals. What is if we want to break this molecule down, what's the best way to do that? If we want to change its rheological characteristics, what's the best way to do it? It begins with understanding the molecule we're working with, and then engineering around it. I think those different technologies are all worth exploring. We're just on the cusp of that stuff right now. And there's so much interest in this from the owner's perspective that there's going to be a lot of opportunity to study that. Now, I'm also a gray hair, So that's a good thing for young people to do too. Um, the younger people who are on board, this is great stuff to study, right?
I
I've
like
always
it.
found too from the younger people who are part of the academy, and if you're an academic, there's the I always say you got the ivory tower academics and then the practitioner academics. And I always put myself in that practitioner academic category. That's where the fun stuff is in our business, right? Be able to work and so the young people on here find practical problems like this and hook up with industry and go to it. Fun things.
Oh, no, I love it. I love it. Now, and one of the things you're talking about, right? We get into the question of sustainability. We think about next generation. We think about what do we do in environmental engineering? You know, we're looking at these organizations that have really been a lot regulation driven. There's now like other
Yeah.
opportunities. There's are adjacent professions that are thinking about green chemistry. Let's just redesign the
Right.
superabsorbent polymers from the start so that they break down
Yep.
differently, right? And so there's a lot of these kind of like adjacent opportunities that we can get into, right? So I think your advice to students or emerging professionals is really powerful. What other stuff would you suggest that they study or work on to be able to work in this space, but be able to work effectively in kind of what the next 10 to 20 years
Yeah.
brings?
Yeah. I think the basic things that we learn are transcend all the different things we work on. Whether it's your different laboratory methods or its treatment process, all those kind of basic fundamentals are fairly constant over time. There's always some things that are emerging. So the thing that I found for the younger generation is, uh, particularly if you're an academic on the side of things, is get out of the university where you're just talking to other professors all the time and talk to people in practice. And that's where this intersection is where there's a lot of exciting things to happen. And whereas an academic, you can add a lot of value, and as a practitioner, you can add a lot of value too. You can bring your practical problems from your industry into the university where you're not only engaging in research, but you're teaching young people how to think and learn and develop hypotheses and test them and how to write. So if I think back on my career, this interaction and the ability to get outside the conventional academic space and work at that intersection with industry, one of the best things I ever did. And it's so much fun too. Travel around the world, solve all these complicated problems and fun stuff,
Yeah, no, it's
Yeah.
fantastic. It's fantastic. Well, Craig, do you have any words of wisdom to leave us with? We have a few more questions. People are saying like, "Hey, can I get a copy of the slides?" There's a few kind of like very, very specific questions. I'm sure you'd be happy if folks follow up with you
Oh,
with
sure.
particular
Yeah. Send
specific.
me an
Hey,
email or,
I-
yep. Yeah, please reach out. And we're working on our journal manuscript on the compositional side of this right now. So I expect we'll have that submitted and I talked to my postdoc. He always thinks it should be faster than I'm doing. But no, it ought to be pretty soon, and we'll be glad to share that with anybody when it's ready. Yeah.
and the slides, we'll have the slides. This will be,
Yeah.
on the YouTube channel. So folks that have questions, but like you said, Craig, all people, we're so appreciative of you having served as the CAPI Distinguished Lecturer this past year, visiting universities, talking with students, being an ambassador of the Academy. You've done such a great job there. I know you'll be open when people reach out to you with an email about a specific technical
Sure.
question on what they've done here. But, on behalf of the Academy and everybody who's benefited, not just from this presentation, but from the work you've done for the past year as an ambassador. Thank you, my friend. Thank you. Thank you. Thank you.
Thank you.
You are a gem and a personal hero, and we're so appreciative to have had you here with us today. So thank you so much.
Thank you, Dan. You're so nice.
Over to you, Marissa.
Excellent. Thank you, everyone, for all your questions. Thank you to Craig for sharing your knowledge with us today. We do have several webinars planned in the near future, so you can go to aaes.org/events and reserve your spot. And just a reminder, if you're not yet a member and you're considering joining the Academy, you can email me and we can discuss membership options. For all board certified individuals, PDH certificates for this event will be sent out by the end of the week. That's all for now. We enjoyed being with you all today. Thank you so much and have a great day.
Thank you all for joining.
Thank you.
Thanks. Bye-bye.
Yeah.